So far you've learned about tile coding, but we haven't connected it back to reinforcement learning yet. Well, the wait is finally over. Today we'll explain how to use tile coding together with linear TD. By the end of this video, you'll be able to explain how to use tile coding with temporal difference learning, and identify important properties of tile-coded representations. The number of active tiles is always significantly less than the number of total tiles. We can use this to calculate the value function efficiently. Recall that with linear function approximation, the value function is a dot product between a weight vector and a feature vector. Let's see what this dot product looks like with a sparse binary feature vector. If we were to multiply the two vectors element-wise, many of the element-wise products will be 0. This means we only have to consider the weights at the non-zero elements of the feature vector. Because the features are binary, the weights at the non-zero features are multiplied by 1. Computing the dot product in the usual way would be expensive. Instead, we can just sum the weights corresponding to the active features. Note that this takes a consistent amount of time because the number of active features is the same in every state. The feature vectors produced by tile coding make querying the value function cheap computationally. Let's look at an example value function with tile-coded features. Suppose we're back at the old pond, with two tilings of 4 tiles each. We've color-coded the tilings, and each tiling square is indexed as shown. If the position of the fish and the weight vector are as shown, what is the value of the fish's position? We can see the fish intersects square 1 belonging to the purple tiling and square 4 belonging to the orange tiling. This results in the following feature vector for this state. Now we simply calculate this state's value with a dot product. The feature vector is binary, so we can just add up the weights at the locations with non-zero features. This gives us a value of 2. Now let's run an experiment with tile coding and compare it to state aggregation. Recall that tile coding is effectively multiple instances of state aggregation, or tilings, layered on top of each other. Our environment is the 1000 state random walk. The states are numbered from 1 to 1000, and all episodes begin in state 500. At each time step, the agent randomly transitions to one of the 200 neighboring states on either side. Overshooting states 1 or 1000 will result in a transition to the terminal state. For example, look at the possible transitions to the left of state 2. 1 will go to state 1, and the remaining 199 will go to the terminal state. Let's talk about how we can use function approximation in this problem. We'll start with state aggregation. Let's use a state aggregation with 5 groups, each corresponding to 200 states. Now let's design a tile coder for this problem with 50 tilings. We treat the 1000 states as an interval, where each tile corresponds to 200 states. Since each tile has 200 states, you might think we only need 5 tiles to cover the full space of 1000 states. However, each tiling is slightly shifted or offset from the others. An extra tile is needed to cover the space left uncovered. Because of this, each of our tilings contains 6 tiles rather than 5. Let's compare these two function approximators with gradient Monte Carlo. The step size parameter alpha is scaled by the number of active features, 50 for tile coding and 1 for state aggregation. Let's look at the results. We plot the value error averaged over 30 runs after each episode. Both agents learn quickly due to aggressive generalization. However, the tile-coded representation is able to better discriminate between states and achieves a lower value error. It's interesting that even though the tile coder has many more parameters, it can learn just as quickly as the core state aggregation. But it also achieves better discrimination because of the small intersections created by multiple overlapping tiles. That's it for today. In this video, we talked about how tile coding can be used to approximate value functions in policy evaluation, and we compared tile coding to state aggregation in a simple example. Next time, we're going to move beyond fixed representations and begin learning representations with neural networks.